Hello, my esteemed viewers here. Welcome once more to my channel. In this particular lecture, I just want to look at a particular example under Kirchhoff's law. We have a circuit diagram here, and in that circuit diagram, we are asked to calculate the current in each branch. That's for part A. Part B says if the circuit remains connected for 180 seconds, we should find the energy delivered to each resistor. Also, we should find the energy delivered by each battery. Then part C says we should find the power dissipated by all the three batteries. Okay, so let's proceed. In this particular figure or this circuit diagram, we discover that there are no currents. Like, currents are not indicated in the diagram. Directions of current are not indicated in the diagram. But looking at the diagram, you have to, if you come across a problem of this nature, all you needed to do is to assign the currents by yourself. First of all, we have three branches. This is one branch here. We have a second branch, the middle branch, and the third branch. So what we are actually looking for now is the current in each of the branch. That is the current flowing through this 2 volt and 4 ohm resistor, the 3 ohm resistor and the 5 volt battery, the 2 ohm resistor and the 10 volt battery. The same current that flows through the 2 ohm resistor is the same current that is flowing through this 5 ohm resistor. So the first thing to do is we first of all indicate the current in all the branches. You indicate the current in all the branches, then you have to assign directions to these currents. Now, the first step to take is that if you look at the batteries, conventionally for any battery, current will definitely flow out through the positive terminal. For any battery, current will flow out through the positive terminal. So in this case, we have the positive terminal of this 2 volt battery here. We have the negative terminal. Here we have the positive terminal, negative terminal, positive terminal, negative terminal. How do I know which is the positive terminal and which is the negative terminal? If you check the battery, the longer point, that's the longer side, the longer terminal of the battery represent the positive terminal, while the short line represents the negative terminal. So having understood this, we can now know the direction of each of the currents. So let's proceed. So having our diagram, if we go by the assertion that current will flow out from the positive terminal of the battery, then in this first branch, our current will be downwards. Why is it downward? Because this longer side is the positive terminal of the 2 volt battery. So if current is coming out of this terminal, it definitely will move downwards. Let us call or label the current here as I1. Now let's come to the second branch. Looking at this second branch, this is the positive terminal. This is the negative terminal. If we say current will come out of the positive terminal, that's conventionally for a battery, then that implies that the current passing through this battery, moving out from this battery, will be directed upwards. So let's call this current I2. Call this current I2. And let us move to the third branch. This is the third branch here. This battery, we have the positive terminal on top and the negative terminal below. So ideally, current will move upwards. And so in this direction, let's call this I3. So we have been able to identify the different currents and their directions. This I3 will move through round and will face this point A. I1 is directed downwards, so definitely it will be moving this way. So in all, we have I2 and I3 entering this node or this junction at point A, and I1 is leaving. So the first thing to do, having assigned the currents and their different directions, we have to apply Kirchhoff's current law to solve for the values of I1, I2, and I3. So Kirchhoff's current law, I'm going to use KCL for short. KCL for short, which is Kirchhoff's current law. So KCL at point A gives us, that current law states that the amount of current entering a junction in a circuit is equal to the amount of current leaving that junction. So if we check I2 and I3, they are entering point A, which is the junction we are making reference to here, and I1 is leaving. So if I2 and I3 are entering into point A and only I1 is leaving, then it implies that the sum of I2 and I3 will give us I1. So we can definitely say applying KCL at point A will give us I1 is equal to I2 plus I3. Let's call this one equation 1 because we'll make reference to it as time goes on. Now, having satisfied yourself with getting the right expression for the current law, you move on to apply Kirchhoff's voltage law in both loops. In this case, we are having two loops here. Let's call this one loop B and let's call this one loop A. Now, in applying KVL, we have to assign an arbitrary direction of current flow. Irrespective of the directions of I1, I2, and I3, we can choose a particular direction for both loops, either the anti-clockwise direction or the clockwise direction. I'm going to use the clockwise direction for my calculation. So I'll just indicate with an arrow to show I'm moving clockwisely. I'll indicate here also with a curved arrow to show I'm moving clockwise. Now let's apply KVL. So I'll say for loop A, Kirchhoff's voltage law, which I abbreviated as KVL for short, Kirchhoff voltage law gives us. Now, the voltage law states that the sum of the potential drops in a closed circuit or in a closed loop is equal to 0. Meaning that we'll find the potential for each component, find the potential for the resistors in this loop A. Of course, this is already the potential here. So if we are moving if we are moving clockwisely, it means this our clockwise direction is opposite the direction of I1, which is passing through the 4 ohm resistor. So the potential drop here is going to be positive. So we say 4i1. Then on getting to this point, remember we are moving clockwisely. Let me use a dotted line. So in this case, we get to this battery and we are coming out, we are exiting through the negative terminal. So the potential there is going to be negative. So we say -2. We move round to this component. The clockwise direction is opposite the direction of I2. So the potential drop here is going to be positive. So say plus 3i2. And on getting to this battery, we are exiting through the negative terminal. So our potential here is going to be negative. So say -5, all equal to 0. We simplify this further. That gives us 4i1 plus 3i2 -2 minus 5 is -7 equal to 0, which gives us 4i1 plus 3i2 is equal to 7. Let's call this equation 2. I might need to split this into 2. Okay, so we are done with loop A. Let's go to loop B. Now take note that we have used 3 ohm resistor and 5-volt battery to calculate for loop A. Does not imply we are going to exclude it for loop B. This is the center branch, so it affects both loops A and B. So starting from this, battery are moving clockwisely. I'm coming out of the positive terminal, so my potential there will be positive. So I say for loop B, Kirchhoff's voltage law gives 5. Getting to this component, I2 is the current moving through this 3 ohm resistor, and our clockwise direction is in the same direction as this current. So we say the potential drop here with respect to loop B is going to be negative. So we say -3i2. Getting to this point, we go around the loop. Getting to this point, this resistor here, the 2 ohm resistor, the current moving through this 2 ohm resistor is I3 and is moving in the opposite direction of the path we have chosen. So the potential drop there is going to be positive. So say plus 2i3. And we are exiting the battery from the negative terminal, so it becomes negative. So the potential there is negative, say -10. Getting to this point, I3 is what is also coming through the 5 ohm resistor and is in the opposite direction of the path we have chosen. So the potential drop across this 5 ohm resistor will be positive. So we say plus 5i3, all equal to 0. We'll simplify further. 5 minus 10 is -5. So say -5 minus 3i2 plus 2i3 plus 5i3 is 7i3. So say plus 7i3 equal to 0, which gives us -3i2 plus 7i3 equal to 5. Let's call this equation 3. Equation 3. Now going further, ideally we are to solve equations 2 and 3 simultaneously, but we cannot proceed because the unknown in equation 2, the unknowns are I1 and I2. But if you come to equation 3, the unknowns are I2 and I3. We can't proceed like this. But we have a bailout in equation 1. So what do? We can choose to eliminate I2 or I3. But it will be much more easier for us to eliminate I3 since we have I1 and I2 here. So from equation 1, we have that I3 can be expressed as I1 minus I2. So therefore, we can substitute this. Let's call this one equation 4. We can substitute equation 4 into equation 3. That gives us minus 3I2 plus 7 into I1 minus I2 equal to 5. If we expand this bracket, we have minus 3I2 plus 7I1 minus 7I2 equal to 5. If we go further, minus 3I2 minus 7I2 is minus 10I2. So we have 7I1 minus 10I2 is equal to 5. Let's call this one equation 5. So we can now solve equations 2 and 5 simultaneously. Bringing them together, this equation 2, 4I1 plus 3I2 equal to 7. This is equation 2 from here. Then equation 5 is 7I1 minus 10I2 equal to 5. It's equation 5. We'll now solve equations 2 and 5 simultaneously. How do we do that? We can consider method of elimination to handle this. And how do we proceed? Is either we eliminate I1 or we eliminate I2. I choose to eliminate I2. So if I'm to eliminate I2, I make sure that the coefficient of I2 in both equations 2 and 5 are the same. How do I do that? I take the coefficient of I2 in equation 2 and use it to multiply every term in equation 5. So I multiply equation is short form for equation 5. Let's start with equation 2. So we multiply equation 2 by 10. Why are we doing that? The coefficient of I2 in equation 5 is 10. So we use that 10 to multiply everything in equation 2. While we use the coefficient of I2 in equation 2 to multiply everything in equation 5. So we start with this. So 10 times 4 gives us 40. So we say 40 I1. 10 multiplied by 3 is 30. And 10 multiplied by 7 is 70. Let's call this one equation 6. Then we use 3, which is the coefficient of I2 in equation 2, to multiply every term in equation 5. So 3 times 7 is 21. 3 times 10 is 30. And 3 times 5 is 15. So we call this one equation 7. Now looking at both equations, for us to be able to eliminate I2 effectively, this is positive and this is negative. So we are going to add both equations. If we subtract both equations, then is a minus sign here. We counter this minus sign and cause it to be positive. So it's going to give us problem. So what we do, since we have a negative sign here, we have to add both equations so that the positive sign against the negative sign will still give us negative. So if we add equations 6 and 7, that will give us 40 plus 21 is 61 I1 plus 30 plus minus 30 is like saying plus 30 minus 30, which is 0. So 70 plus 15, that gives us 85. So our I1 will simply be 85 divided by 61, which leaves us with 1.393 ampere. So our I1 is 1.393 ampere. Let's move on to solve for I2 and I3. Now recall equation 2. Equation 2 is 4I1 plus 3I2 equal to 7. That's equation 2. And we have solved I1 to be equal to 1.393 ampere. So all we need to do is simply substituting I1 into equation 2. That gives us 4 into 1.393 plus 3I2 equal to 7. We proceed further, we have 5.572 plus 3I2 equal to 7, and 3I2 equal to 7 minus 5.572. So that 3I2 equal to 1.428. If we simplify further, I2 will give us 1.428 divided by 3. So that I2 gives us 0.476 ampere. So having obtained I1 and I2, we can then proceed to solve for I3 using equation 4. Recall equation 4 that is I3 equal to I1 minus I2. Recall I1 is 1.393 ampere. I2 is 0.476 ampere. So that I3 will eventually give us 0.917 ampere. So let's look at part B. Part B requires us to calculate the energy dissipated, the energy delivered to each resistor if the connection remains constant for 180 seconds. So energy delivered, energy E is expressed as IVT, or we can also express energy as I squared RT. So for the 4 ohm resistor, we have that E is equal to, if we check our circuit diagram, you go over to the circuit diagram. The 4 ohm resistor, the current passing through the 4 ohm resistor is I1. So we say I1 squared times RT, which is I1 is 1.393 ampere times the 4 ohm resistor times the time 180 seconds. That gives us 1397.12 joules. For the 3 ohm resistor, we have that E, the current passing through the 3 ohm resistor from our circuit diagram is I2. So we say I2 squared RT, which is equal to I2 is 0.476 ampere times 3 ohm times 180. So that this approximately equal to 122.35 joules. Let's move on. For the 5 ohm resistor, we have that the energy E is equal to, recall that in that 5 ohm resistor, the current passing through that resistor is I3. So say I3 squared times RT, which gives us I3 is 0.917 ampere times 5 times 180. That gives us 756.80 joules. For the 2 ohm resistor, the energy is I3 squared, because the current passing through the 2 ohm resistor is I3. So I3 squared times RT 0.917 squared times R is 2, time is 180 seconds. That gives us 302.72 joules. Then the energy delivered by each battery, for the 2-volt battery, we have that E is equal to IVT. For the 2 volts, I is I1. I1 is what is passing through the 2-volt battery. So we say I1 times VT, which equal to 1.393 times 2, which is V, times 180. That gives us 501.48 joules. For the 5-volt battery, we have that the energy is equal to, if we check the circuit diagram, the 5-volt battery, the current passing through that 5-volt battery is I2. So we say I2 times VT, which is I2 is 0.476 476 ampere times V, which is 5, times T, which is 180 seconds, and that gives us 428.40 joule. For the 10-volt battery, we have that E is equal to the current passing through the 10-volt battery is I3, so we say I3 VT. I3 is 0.917 ampere. V is 10, T is 180. This leaves us with 1650.60 joules. Then part C says we should find the power dissipated by the battery. So for part C, for the 5-volt battery, power is equal to IV. Recall that the current through the 5-volt battery is I2. So we say I2 times V, which is I2 is 0.476, sorry, times 5. This gives us 2.38 watts. While for I3 we have 0.917 ampere times 10. This gives us 9.17 watts. And for the 2-volt battery, we have power for the 2-volt battery is equal to I1 is the current passing through the 2-volt battery. So say I1V. I1 is 1.393 and V is 2 volts. And so this gives us 2.786. We can just approximate this to 2 decimal places as 2.79 watts. I hope you enjoyed this solving. Remember to drop your comments in the comment section, subscribe to my page, and of course, share my videos and like my videos. Thank you.